What is frequency resolution in FFT analysis? Imagine trying to listen to a song and being able to tell if two notes are played very close together. That's what frequency resolution in FFT analysis helps us do in signal processing. When we analyze signals in the frequency domain, we want to see distinct peaks for different frequencies. The question is, how close can these peaks be and still be seen as separate? That's where frequency resolution comes in. It is the smallest difference in frequency that the FFT can distinguish between two signals. Think of it like the sharpness of a camera lens but for frequencies. The finer the resolution, the clearer the separation between two close frequencies. In digital signal processing and electrical engineering, the key factors that determine this resolution are the sampling rate and the number of samples we analyze at once. The sampling rate is how many times per second we record the signal, measured in hertz. The number of samples is how many data points we include in our analysis. The mathematical formula for frequency resolution is the sampling rate divided by the number of samples. So, if you have a sampling rate of 1,000 samples per second and analyze 1,000 samples at a time, your frequency resolution is 1 Hz. That means you can tell apart two signals if they differ by at least 1 Hz. If you increase the number of samples, say to 2,000, your resolution improves to half a Hz. The length of the data block, or how long you record the signal, also affects resolution. Longer recordings mean more samples, which lead to better resolution. But there is a trade-off. Longer data segments mean slower updates in real-time analysis. If you want to detect small differences in frequency, you need a longer window of data. Conversely, shorter data segments give faster results but less detail in the frequency spectrum. It's also important to note that the maximum frequency you can analyze is limited by the sampling rate. According to the Nyquist theorem, the highest frequency you can measure is half the sampling rate. This is called the Nyquist frequency. If your sampling rate is too low, high-frequency signals will be distorted or cause aliasing, which makes your analysis inaccurate. In practical applications like vibration analysis, communication systems, or control systems, the ability to distinguish close frequencies is vital. For example, in machinery monitoring, identifying tiny differences in vibration frequencies can predict failures early. In communications, separating signals that are close in frequency helps avoid interference. To sum up, frequency resolution in FFT analysis is about how closely spaced two signals can be and still be seen as separate. It depends mainly on the sampling rate and the number of samples analyzed at once. Improving resolution means analyzing longer segments of data, but that can slow down how quickly you get results. Understanding this balance helps engineers design better systems for analyzing signals accurately and efficiently.